like to thank Professor Charles for giving me a great opportunity to present my work here. Basically, this work has been done in my PhD and postdoc period. This is the outline of my talk today. Basically, I just divided my talk in two parts. The first one is control of self-assembled nanopatterns. And the second part is I will introduce a new way to fabricate nanoparticles using block polymer template. So I will start with the block polymers. Already Professor Lee and Son introduced block polymers. And also, I'd like to introduce how we actually control the orientation of block polymer microdomains. And also, I'll introduce new driving forces we have developed, which includes fractional solidification and topographic pattern-assisted fractional solidification, and finally the pattern control by the sulfur lithography. In the second part, I'll show you we actually used the new types of block polymer to fabricate nanoparticles on surface in a very simple way. So let me start with some examples of the nanostructures we found in nature as well as synthetic way. So I just summarized, I just cropped some beautiful pictures in this slide actually to introduce the nanostructures we found in nature. The first of all, the silicon dioxide, silica colored actually beautifully self-assembled. And then if you look at this macroscopic phenomenon, this optical micrograph shows the variety of colors from this microstructure. So if you change this microstructure, the size of the particle, then you can change the color of this structure. So we just call this one called like a photonic crystal. And also we have the DNA, which has a nanoscale dimension. A lot of people recently actually used the DNA to apply this DNA for some specific applications. Quantum dots and the single wall carbon nanotube also another examples of the nanostructures. And if you go to the supramolecular synthesis, the Professor Stu actually Northwestern University actually synthesized these types of mushroom structures. If you can imagine, we can self-assemble this structure for some other the macroscopic super lattice structure. Maybe we can use this structure for some specific application. In nature, this abalone shell has a specific, a particular, a very super mechanical property due to the microstructure, as you can see in this scanning electron microscope. This abalone shell has two different types of the composites, organic and inorganic composite that produce a very large amount of toughness of this material. So among all these kind of examples, today I'd like to focus on the block polymer, which synthetically fabricated, and also is pretty useful in various ways. I'm not going to spend a lot of time to explain what the block polymer is, because previously a lot of the Professor Lee and Professor Son actually introduced this block polymer. But mainly, actually, in the simplest case, diblock polymer has the molecular architecture like this. And due to the incompatibility, this A polymer and B polymer don't like each other and then tend to phase separated. But due to the physical connection in the middle, this block polymer undergoes microphase separation instead of having the macrophase separation normally observed in the polymer gland system. So block polymer has advantages. One of those advantages is we have a various microstructure. If we change the chain length, so-called the volume fraction of this A and B polymer. And also the size of microstructure is nanometer scale, usually 10 to 100 nanometers. And also we can tune the microdomain size, changing the length of polymers. So we have this slide actually shows when we actually change the length, relative length of the block polymer, then we can create, starting with the lamellary structure, when we have a 50% A and 50% B, to the 20%, less than 20% A, we can create various microstructure, thermodynamically stable various microstructure. In addition, in the middle, actually, where we showed the narrow range of this range, we can create three-dimensional bicontinuous structure as shown in this scanning electron micrograph. So one thing actually I'd like to point out here is using the conventional patterning techniques such as photolithography or the other lithography technique, it is very difficult to fabricate this kind of three-dimensional self-assembled structure. That's the one of the advantages of blockopolymers. Again, in blockopolymers, recently a lot of people are interested in this blockopolymer because blockopolymer can be used for the nanotechnological applications. So I will just spend a few minutes actually to explain what kind of examples, what kind of applications using these blockopolymers. As you may know, we can use the blockopolymer as a photonic band gap material. This part actually already briefly Professor Lee mentioned. In this particular case, polystyrene and polyisoprene diblockopolymers self-assembled into the multi-layer structure. So this multi-layer structure can be a mirror actually, in case changing the dimension of this dielectric stack, we can control the reflection light range. In this particular case, we can reflect this about 450 nanometer range. We achieve almost 100% reflectivity using this self-assembled structure. Another example of using this blockopolymer is nano pattern transfer application. We just call this one nano lithography template application. In this particular case, the people use the sphere forming blockopolymer and then self-assemble and then remove this one using ozone treatment, ozone or UV treatment, and then using the reactive ion etching, and then transfer this pattern to the substrate you're interested in. In this case, Lee actually used the gallium arsenide substrate to fabricate the gallium arsenide, the regular dot structure. So we can use the blockopolymer self-assembled structure to fabricate this kind of dot structures. In this case. I have another examples using the blockopolymers. I put the three more examples here. So blockopolymer can be used nanoporous, nano-relieved ceramic precursors. In this particular example, people use the silicon-containing blockopolymers. So they just use the self-assembly using the polymeric property. So the polymer is self-assembled, then make the three-dimensional bicontinuous structure, and then did the heat treatment. So it's during the heat treatment, the organic part actually is burned out, and then the silicon, the Si part actually combined with oxygen, and then convert to silicon dioxide. So finally, they could produce the three continuous, the nanostructure of silicon material, which is the ceramic materials. So in this case, using the polymeric material to make the nanoporous ceramic membranes. As actually Professor Lee actually mentioned in this part, and also Professor Son also talk about this one. So the people try to make the nanocomposite using blockopolymers that incorporate nanoparticles or grow the nanoparticle inside blockopolymer patterns to make the organic, inorganic, hybrid nanocomposite materials. So lastly, this example is similar to what I explained before using the template, using the blockopolymer as a template. But in this case, people use the tungsten, the substrate, instead of using the gallium arsenide. So if you use the tungsten is magnetic material, so we can produce this kind of single dot of the magnetic material. Hopefully, we can use this pattern for the magnetic media storage application. So, but in reality, if you want to use the blockopolymer, we have to overcome one thing, which is orientation and control of the microdomain structure. This is typical microdomain structure of blockopolymer when you have when actually they just self-assemble. So this is thin film and the bulk film. Even though we actually did the long time heat treatment, still we have a grain boundary and the point defect as I indicated with the arrows. So this is the motivation of our research as well as the objective of our research. How actually we can create the long-range ordering, how we can control the microdomain structure and the block of polymers for real application. So let me just talk about how we can control the orientation of block of polymers. Already a lot of people have actually work on this area. So main idea to control the microdomain orientation is we just put some external field into this self-assembled system, and this external field can couple to the microdomain structure. Finally, we can reduce orientation, or we can control the microdomain orientation. So we can easily think about external forces such as mechanical control field, like compression or extension or shearing and so on. And also we can think about electric field and temperature gradient and magnetic field and so on. But if you're interested in thin film application, which I'm interested in, we have to consider the surface property. Because in thin film we have a huge amount of surface area, so somehow we have to control the surface area. Usually surface interaction is usually dominant to control the orientation. So, for example, we have to think about how we control the thickness, and also confined films, boundary condition, how we control the boundary condition in the thin film. Also, the people use the chemical or topographic pattern structure to control the structure, and the solvent evaporation and graphite detection, and also the wetting, de-wetting, also one of the examples, one of the external force to control this, control the orientation. So among all these kind of driving forces, today actually I'd like to introduce new driving forces we have developed. First one is directional solidification, and the second one is topographic pattern-assisted directional solidification. Finally, I will introduce the pattern control by soft lithography. Let me start with the directional solidification first. This slide actually shows there's nothing to do with the polymer. This directional solidification actually came from some similarity of the metal system. For example, this one is lead-cadmium alloy system. This is typical phase diagram of the metal system. So A and B metal, when actually the temperature is high enough, they just mix together, make the one homogeneous phase. But temperature goes down when actually temperature passes through the eutectic temperature. This liquid phase becomes two different solid phase, which is alpha and beta phase. But due to the cooperative diffusion at the interface between liquid and solid phase, this alpha and beta phase propagate together and then create directional microdomain structure. We just call this one the directional eutectic solidification. So this is typical example of eutectic directional solidification. So in this case, lead and cadmium actually directionally crystallize together and then create the regular structure. So we actually adopt this idea to our system with the block of polymer. So we're going to use the block of polymer as a one solid state. And also we need another solid state to make the directional solidification. So another solid state is, for example, we use the benzoic acid, which is crystallizable solvent. So this is chemical structure of benzoic acid. So the benzene has a COOH acid group. When actually they just crystallize, they have a hydrogen bonding and then make the beautiful single crystal. This is a crystallographic dimension of benzoic acid crystal. And when actually they crystallize, they just expose the surface, which is 001 plane of the benzoic acid. So we can expect the block of polymer sitting on the 001 plane of benzoic acid. So we found very interesting phenomena, actually, accidentally say. We use the crystallizable organic solvent, for example, benzoic acid. The melting temperature of benzoic acid is 123 degrees C. So when actually above this temperature, this benzoic acid becomes liquid. So we found at liquid state, benzoic acid can dissolve can dissolve the Blocker polymer. So above the melting temperature of benzoic acid, we found a homogeneous mixture stage. So it's homogeneous liquid. And since we are interested in the thin film application, we just confine the geometry by using this substrate. So initially we have homogeneous mixture at high temperature. And then when we actually decrease the temperature, the benzoic acid starts to crystallize. But when benzoic acid crystallizes, benzoic acid has a fast growth direction, which is B-axis. The benzoic acid tend to crystallize very fastly, actually along the B direction of their crystals. So initially, benzoic acid is a solvent of Blocker polymer. So when benzoic acid crystallizes, the Blocker polymers don't have the solvent, so they tend to the phase separated. So since benzoic acid crystallizes directionally, the Blocker polymer film also followed that direction, and then phase separated, and then sample assembled. That's actually the phenomena actually we have, starting with the liquid phase, homogeneous liquid phase becomes directionally solidified two different phases. This phenomena is pretty much similar to the traditional detected directional solidification found in metal system. That's why we just put this name, the directional solidification. Experimentally, this method is pretty much simple. We just start with just a simple casting of the Blocker polymer on any substrate you're interested in. In this case, we use the glass substrate. We can use the silicon substrate or any other substrate too. And then we put the powder of the solvent, which is benzoic acid. At room temperature, benzoic acid looks like powder. It's because this benzoic acid is crystal state. We just cover the cover glass and then increase the temperature above the melting temperature of the benzoic acid, produce the homogeneous liquid, and then crystallize benzoic acid. Just the process is done. Finally, we can just characterize the Blocker polymer structure with this one. So this is typical, actually, glass substrate we use in the laboratory. As you can see, when actually the benzoic acid crystallized, we actually used some seed crystal here or coat the contact to produce directional. Only one single single spot is the nucleation point. So the benzoic acid directionally crystallized, as you can see here. If you look at inside with the optical microscope on the polarized light, as you can see, we have a beautifully crystallized, very flat and large single crystal of the benzoic acid. So this surface is going to be 001 phase of benzoic acid. The color difference in this optical micrograph is the thickness variation of the benzoic acid crystal. But as you can expect, we can expect the Blocker polymer film sitting on the flat, the single crystal. We actually used a variety of the examples of the Blocker polymers. We start with the polystyrene and polymetacrylate PMMA. The ratio is about 50%. We expect the lamella forming Blocker polymer. So we just did the benzoic acid process, directional solidification. We found the microstructure is well organized and then has a very beautiful orientation. This schematic diagram shows the orientation of this lamellae sample of polystyrene and PMMA. So we can use the different Blocker polymers, not just the lamellae forming Blocker polymers. We can use the cylinder forming Blocker polymer too. In this case, we use the polystyrene polyisoprene. Polyisoprene actually form the cylindrical domain. The size of cylinder is about 20 nanometers. And the film thickness is about 50 nanometers. As you can see, all the cylinder actually oriented along the B-axis of benzoic acid due to this directional solidification. So we found that this process worked. And but another thing actually we just consider is film thickness effect. So when you can just imagine. Now in this case, actually cylinder actually tend to lie down. Cylinder has a more entropy to lie down like this. But when we decrease the film thickness, say below the 20 nanometers, but in this case we have to consider boundary condition. But in simple case, if you just decrease the film thickness below the 20 nanometers, which is cylinder size, cylinders no longer actually tend to in plane shape. Cylinder structure actually they break up and then tend to standing up to the on the substrate. So in order to see this effect, we just make the thinner block of polymer film and then did the same process, fractional solidification. So we use the same block of polymer, polystyrene, polyisoprene, the same block of polymer. Only difference is we just change the film thickness. So as you can see, we have a large area orientation, and the cylinder is standing up. So if you change the thickness, film thickness, we can control the orientation of the block of polymers. So now, I just move to the next part. So still actually we need to control the large area orientation for the real applications. So in order to do that, actually the one idea is we have to combine more than 2 driving forces for the better control. So that's actually the main idea, the combination of more than 2 driving forces. And the idea, actually specific idea we have is to combine the conventional patterning methods such as the lithography method and the self-assembly. So if you look at this dimension, so we can control easily the pattern size in this area, like a centimeter and a millimeter and up to 1 micron size, we can easily control the pattern structure using the lithography method. But below the 100 nanometer, it's hard to make the pattern structure using conventional method. Hard to make the conventional method. So in this region, actually, we just use the self-assembly. So if you just combine these 2 parts, hopefully we can control in this area using the lithography method, and below this area, we just use the self-assembly to make the global orientation of the pattern. So the first example is we just use the topographic patterns. So this one actually fabricated by this conventional photolithography. So we just make the holiness. So when is the training? 15 minutes. All right, that's enough. So we just fabricated pattern structure using the photolithography. As you can see, this one is 2 micron size the mounting and 4 micron the periodicity. If you look at the pattern in this direction, so we have a mounting like this. So the height of this mountain is about 30 nanometers. So we just combine this pattern structure with the directional solidification I just introduced before. So the idea is when actually the benzoic acid crystallizes, like this, make the flat surface, flat single crystal, and we use this topographic pattern structure. The block of polymer actually confined in between these 2 substrates, and they just undergo film thickness difference, the variation of the film thickness. For example, if you just control the thickness carefully, then we can create about 50 nanometer film in this region. So since actually this mountain has a 30 nanometer height, we can control the film thickness here is about 20 nanometers. So as I explained before, we can create, in this region, this matrix region, we can create just the in-plane cylinder. But under this mountain region, we can control the orientation, which is standing up cylinder, which is more useful for the real application. So for that, actually, after we just fabricate this film structure, and then we just did the oxygen plasma reactive ion etching to remove the selectively this selective domain to fabricate the membrane, the nanoscale membranes. That's what we did. So as you can see, this one is a large area picture. It's more than 100 micron area is easily fabricated using this, controlled using this this method, the combination of these 2 different forces, like a pattern, the photographically fabricated pattern and directional solidification. So this is large area picture. If you look at inside of this area, then as we expect, the matrix region, the cylinder actually oriented along the B-axis of benzoic acid, directionally phase separated. And then, as we expect, on the mountain region, the cylinder actually the hexagonally packed and then standing up due to the thickness variation. So after actually we did the reactive ion etching, oxygen plasma reactive ion etching, we just conformed. We create the nanometer scale whole structure. Especially we are interested in the pattern structure, pattern area. This height contrast AFM image shows the dark and the greater the contrast in this picture. Next one is we can somehow use the soft lithography, another actually conventional method, to make just the micron scale pattern, micron size patterns. So the much easier way than the photolithography method. Let me just briefly explain how we actually control, how we make this pattern using the soft lithography. So we just use the mask and then photoresist actually on top of any substrate you're interested in, and then expose and then make the pattern. Up to here is pretty much similar to the photolithography. And then the only difference is we just pour the pre-polymer, which is polydimethylsiloxane, which is the elastomer. And then pour the elastomer and then cure. And then after we just remove the elastomer, we create the so-called we just make the stamp of the PDMS. So once we have a stamp, we can apply this stamp for various applications. For example, micro-contact printing and micro-molding in capillary. We just call this one mimic. And also we can use this stamp for the micro-transfer molding and near-field lithography. So today I'd like to use micro-molding in capillary using block-polymer. So the idea is, this one is also one of the examples of how we actually combine these two driving forces to control the nanoscale self-assembled structure. So first we just fabricate this pattern structure, this stamp using soft lithography easily. Then we can put the solution of block-polymer solution in front of this channel. And then since this channel is too thin or too small, it has a capillary force. So we have a flow field. The flow field actually into this channel. So block-polymer actually somehow suck into this channel and then self-assemble. So we have a flow field, one driving force which is flow field, and then another driving force which is boundary condition. Somehow we can control we can make this surface, this PDMS surface, hydrophilic or hydrophobic using some surface chemistry. So finally, we hope we can control this large area, the pattern, using the soft lithography, and inside this pattern, we can control the orientation using block-polymer. So this is kind of preliminary, the data tree I just made. As you can see, we have easily create regular pattern structure using the mimic, which is the micro-molding in capillary. So easily we can create the regular structure of the block-polymer. And also if you look at this area with the AFM, the nanostructure of the block-polymer is pretty much hexagonally packed and then aligned in this direction. So this is preliminary result of using this method. The problem actually I have is, since actually we use the polymer solution, block-polymer solution, when actually the solvent evaporates in the channel, it is very difficult actually to control the film thickness. So it's somehow on the wall side, on the boundary side, actually the film thickness is thicker than in the middle, something like that. So we have to somehow overcome this problem in the future. Okay. Let me just switch the topics a little bit, and then I'll just introduce briefly how we actually create nanoparticles on the surface of the block-polymer pattern. So this one actually worked done by Hashimoto, and then they just produced the nanoparticle inside the block-polymer in both systems. And Professor Son actually did a beautiful job actually on this area. He actually created the nanoparticles inside the block of polymer. We are interested in actually forming the nanoparticles on the surface of the pattern. But eventually we have to, since we are interested in the patterns, nano patterns. So recently actually I found the paper actually published in Nature is Lopez actually used the block of polymer and then evaporate the gold particle or gold particles on top of this block of polymer pattern, and they just create the nanoparticles on the surface of block of polymer. So we used a little bit different approach. Actually, we just collaborate with Professor Fraser actually in University of Virginia. She's a chemist. She's very good at making polymers. She's interested in actually this kind of geometry, this kind of polymer with this kind of geometry. So-called the metal complex. She just used the functionalized metal complex initiator for the leading polymerization. And then this one actually very interesting because it has an ion. It's pretty much mobile ion actually. The coordinate. It has a coordinate bond inside. So it's ion centered 6-arm multi-block of polymer. So each one actually diblock of polymer A and B, A, B. But it has a 6-arm, and then in the middle we have ion molecules. So this diblock has a microphase separated because this block is hydrophilic and this block is hydrophobic. So we have a microphase separation into the cylindrical pattern. And hopefully we can create, the idea we have is this block of polymer self-assembled into the cylindrical structure. When we control the film thickness, hopefully we can create this standing up cylinder. And the ion actually is sitting inside of this cylinder, actually confined in the cylinder. And then we did the heat treatment. So ion actually diffused out and then combined with oxygen in the environment and then create ion oxide. But at this point actually we don't know exact composition of ion oxide, but we did the EDX, the energy dispersed X-ray method to find most of the composition is formed by the ion and oxide, but we don't know the exact composition. But this one is actually using the homopolymer. This is not block of polymer. So we just use the homopolymer with the ion center. So as you can see, the size of the nanoparticle is pretty much, the size distribution is not narrow enough. So when we use the block of polymer, so this block of polymer is sitting on top of the pattern structure. This one is unstained sample. This one is stained sample. You can see the microstructure as well as the nanoparticles. The nanoparticle size is pretty much narrow. It's about 20 to 30 nanometers. But the reason actually we have very few nanoparticles is total amount of ion actually in the block of polymer is very small because we have a 6-arm of the block of polymer and then only 1 ion atoms actually in the middle. So in order to conform the nanoparticles sitting on the surface, we did the AFM experiment. We found that this high contrast, the nanoparticles are sitting on the surface. Okay. So let me conclude my talk. I present 2 parts. This first one is control of block of polymer microdomain, and second part is one way to make the nanoparticles using block of polymers. I introduced the directional solidification and topographic pattern-assisted directional solidification and the pattern control by software lithography. And in this section, we use the polyoxazolene, which is the name of the block of polymer I just mentioned, using this block of polymer and then make the nanoparticles on the surface. In the future, we have to work on a little bit harder and then make the more precise addressable patterns for real device fabrication. That's the main goal. Right. Thank you for your attention.